1.5 is the combinations of functions. What we'll talk about here is how to add, subtract, multiply, and divide functions, and then also the composition of one function within another function. So your arithmetic combinations of functions, so this is just recognizing function notation and what this means. So if you see something that says f plus g of x, it really means you're just adding the function that's f of x to the function called g of x. So the difference, f minus g of x, just means f of x minus g of x. And then you also have the multiplication and the division. So if we want to find the sum and difference of two functions, this first one says find f plus g of x. So remember that f plus g of x really just means f of x plus g of x. So our f of x function is 2x plus 1. Our g of x function is x squared plus 2x minus 1. And so when we combine like terms, we get x squared plus 4x. So for the second part, when we have f minus g of x, that just means f of x minus g of x. So our f of x is still our 2x plus 1, but now you're going to subtract x squared plus 2x minus 1. And make sure you put that in parentheses so you remember that you need to distribute that negative. So you really have 2x plus 1 minus x squared minus 2x plus 1 when you distribute your negative. And then when you combine your like terms, you get minus x squared. The 2x's simplify, and you just are left with plus 2. So in our next example, we have finding the quotient, which means you're dividing. So if we're finding f divided by g of x, we're going to take our f of x and divide g of x, which means you have the square root of x over the square root of 4 minus x squared. Okay. So now don't be tempted to simplify the 4 and the x squared under the square root. You have a binomial, so you're not allowed to simplify them separately. So it just has to stay 4 minus x squared under your square root. So this would just be your answer. Or if you wanted to, since they're both under a square root, you could put it all under one square root and write it as x over 4 minus x squared. So the second part says find the domain. So when you find the domain, we have to look at the two separate parts. We know that the domain for f is reals greater than or equal to 0, since it's the square root of x. When we have this 4 minus x squared, if we were to solve for x, we would get plus or minus 2 when it equals 0. So that gives us those endpoints. Remember, we had one of these before where it's that just top half of a circle. So the domain for this would be that negative 2 has to be less than or equal to x, which has to be less than or equal to 2. And so when we combine these two, and remember the top one, we had that x has to be greater than or equal to 0. So you have to combine the two domains to make them work for everything. And so if you think about this on a number line, if we go negative 2 to 2, for that first part, or the denominator. And then for the numerator, we had 0 to infinity. So your domain then is that part that overlaps. So on this one, then we would say that our domain is anything from 0 to 2, including both of those, because those are this area right here is the only part where both functions that we divided, their domains overlapped with each other. So then the second part of this section is talking about the composition of functions. So when we do a composition of functions, it's when we plug one function into the other function. So if we have f of g of x, that means that you're taking the g of x and substituting it into the x in the f function. So if you were to do that, you would get that x plus 1 squared. Okay, you'll also see it notated as f of g. This little open circle just means that composition of f of g. but it would mean the same thing as if you wrote it that way as well. So your definition of composition is we have this notation, f of g of x is equivalent to f of g of x, just those two different notations. And it really just means that we're taking the domain of that composition is the set of all x's in the domain of what you're substituting in, so g, such that g is in the domain of f. So really we have to look at what we ended up with for the domain and what we also plugged in and make sure it works for everything. All right, so when we look at example 5, first we have to find f of g of x. So that means f of g of x. So we're taking whatever g equals, x minus 1, and we're substituting in for this x. So we would have the square root of x minus 1. And then the second part says, if possible, find f of g of 2. So f of g of 2 means that we have to substitute in the 2 for our x value. Or you could think about it, you do the g of 2 and then you substitute it in. So we get the square root of 2 minus 1, which equals 1. And if we do f of g of 0, we would get the square root of 0 minus 1, which would be the square root of negative 1. Right, so we know that for that part, then that doesn't work because we get that imaginary number. Or you could think about it as that it doesn't work because if we were to look at the domain up here, we know that the domain of our composite function is anything from 1 to infinity. So if we wanted to plug in a 0, 0 isn't part of our domain. So we would just say not part of the domain. So for example 7, we're going to find the domain of a composite function. And they're telling us to do the composite of f of g. So that means that we're plugging this whole function for g into this x value. So f of g would equal the square root of 9 minus x squared, that's when we just substituted in right here, and then minus 9. And so if we simplify that, we get 9 minus x squared minus 9, since the squared and the square root simplify. And so we're left with negative x squared. Now it says find the domain, so it seems like our domain should be all real since we just have a parabola. But when you find the domain of a composite function, you have to consider the two functions that make up your composite function. So if we look at this first part of the function, the f, we have all reals for this domain. But if we look at this function right here, this function's domain is just negative 3 to 3, right? Because we have that 9 minus x squared. And if we solve for when 9 minus x squared is 0, we would get x equals plus or minus 3. So those are those endpoints. So if we were finding the domain of the composite, we would have to use the negative 3 to 3, since that would work for all the functions that make up that composite function. And then our last example is identifying a composite. So looking at a function and thinking about what two functions could we have written that would have created this composition of two functions. So usually when you start out, so we would say that h of x is a composite of two functions. So maybe we would say f of g, which you could think about as like f of g of x. So when we're coming up with the two functions, kind of the trick is to look at h of x and say, well, what is its parent function? So its parent function in this case is 1 over x squared. So what we do is we let the parent function be the outside function, so the f of x. And so if f of x is 1 over x squared, then what did you substitute in for this x to get this? And so we would know that we substituted in x minus 2. And so if you were to go back and go backwards and do f of g of x, if we took this x minus 2 and substituted it in, we would get this h of x.